Alright, we are finding derivatives and we're going to be doing it implicitly. Implicit differentiation is what we call this. This is the graph to our equation, which I'm going to show here in just a minute. And we're going to be concerned with the point 1, 1 on the graph, which is right here. Now, as you can see here, this red line running straight across, this is just a segment here of the tangent line. And of course, the slope of this tangent line, this is a horizontal line. And so the slope of the tangent line has slope 0. So if we plug 1 into the derivative, what should we get out? Well, we should get the slope of this tangent line, which happens to be 0. And this is really kind of a special point right here. This is called a maximum in a neighborhood. But we'll be talking about that later on in the applications of derivatives. Of course, there'd be another one over here and a minimum down here. But okay, so let's reveal what this equation looks like. Oh, and by the way, there's a name to this particular curve here, and it's known as a bifolium. It's kind of pretty, got lots of symmetry. And it follows under an even function. We can go back and remember what even functions are. But anyway, all right, let's take a look at it. Okay, so here's the point, 1, 1. That's what we're concerned with on the graph. And here's our nice, lovely equation. Now, this is definitely a good example of why we have to use implicit differentiation, because this is not in explicit form, which means we are going to have a heck of a time trying to solve for y in this problem and getting it in terms of x. And so that's the reason that we use what's called implicit differentiation. So here we go. We're going to take this 2, bring it out front, rewrite everything in parentheses, subtract 1 from the exponent. Then what we're going to do is take this chain rule part. We're going to take the derivative of the inside, bring it out. So the derivative of x squared is 2x plus the derivative of y squared. You take the 2, bring it out front, rewrite the y, and remember we have to tack on a y prime. Okay, so that takes care of the left side of the equal sign. Let's look at the right. Well, we've got a product here going on. So what I'm going to do is I'm going to take the derivative of 4x squared first, and that's going to be 8x, and then we rewrite the second, plus, rewriting the first, 4x squared, rewrite that, and then the derivative of y, which is 1, but I don't write 1 here, and then remember we have to tack on a y prime next to it. Now remember, I'm using y primes and not dy dx. You could use dy, you could write dy dx here if you want, whatever you want to do. Alright, now what I'm going to do here is do some do something. I don't know what I'm doing. What am I doing down here? Oh, it looks like okay, I'm trying to get rid of this 2, and so I'm multiplying both sides by a half. I've got brackets here, which means I'm multiplying a half times all this stuff inside brackets. I don't know why I'm doing this. I should have just plugged the 1 directly in and then solved for y prime, but whatever. Alright, so take a half, multiply, that gets rid of that 2, and then of course we got a half of 8, which gives us 4, and a half of this 4, which gives us 2. Alright, what a mess. Looks like I do some foiling here, x squared times 2x, and right, multiplying this stuff across. Okay, follow all that. Anyway, FOIL, first, outer, inner, last. Right, and then nothing we can do over here. I don't know. Some crazy stuff. I'm trying to get y prime. I get y prime over here to the left hand side. Take some stuff over here. Factor y prime out is what I do. And then divide both sides by this whole mess here, where we end up getting y prime is equal to, and I could have factored a 2 out of the top and the 2 out of the bottom. I didn't. I don't know why. And then I went ahead and plugged the 1 in for x and y, and then did the arithmetic.